Welcome to this video to get you ready for MasterCheck 12.2. We're going to be talking about, I guess these are three types of diagrams, and they're all kind of showing the same thing. They're showing potential, the elevation, if you will, if you're thinking of like a topographical map. So for a piece of land, but we're doing the electrical version where instead of elevation, we're talking about potential versus position. So the one on the left here, you can imagine that this would be a negative charge plate, and then up here would be a positive charge plate. And you can see how there's this big slope in between the positive and the negative, and to the right over here is maybe a more traditional kind of a diagram where we've got here's the positively charged plate, here's the negatively charged plate. You'll notice that from here to here, it's not the exact same diagram because the position of the plates got dropped. But we could kind of think of this one here as just this side of it, because I can see here that these equipotential lines look quite evenly spaced. And that's the main thrust here about this lesson here, is that these lines here are nicely evenly spaced across. And just to further show that, this could be for this diagram over here, where I'm talking about point A, and here I'm talking about point B, and I can say, okay, the potential at A is quite high, and the potential B is quite low. It drops from A to B, just like it would drop down this hill over here. And because these lines are evenly spaced, you can see the slope of that is constant. It's a nice straight line. So when we're talking about how do I know that the field is uniform, and really I'm referring to this diagram over here. In this diagram, how do we know that the field is uniform? It's because of those equal potential lines. Those purple lines are evenly spaced. So I mean this 1 and the 2 and the 3 and the 4, those 4 lines have nice even jumps in between each other. So and just remember, you can think of how strong the field is. It's similar to this idea to a slope on a potential diagram. Whether you're looking at a cool 3D one here, you can say this has a nice even slope, or if you're looking at a sort of a two-dimensional version of one, or if you're looking at this one, you can sort of imagine it's going from uphill to downhill. All right, here it says for the next question, calculate the electric field strength. Well, let's just think, how would we answer a question like that? Electric field strength is usually in newtons per coulomb. In other words, what kind of force on a coulomb. Or we could also use the units about the difference in potential per meter. I'll put the units here, per meter. That's the other way to think about it. In other words, how much does the potential change? How much, like it's this idea of slope here, right? How much does it drop? This would be the delta V. This would be the change in potential. And then this would be, you know, the distance. It's kind of like rise over run. So I put in a distance here of 10 centimeters. So if we're going to calculate the strength, we can say, well, it's 10 centimeters. So this would be 10 centimeters on the bottom. And what's the drop in potential? I didn't make one up. Shall we make one up? How about we're going to say it's 50 volts. So in other words, let's say that in this diagram, the difference in potential is 50 volts. Okay, so that would be 50 volts over 10 centimeters. So I could say 50 volts divided by, I have to put that into meters, so that'd be 0.1 meters. So I would get 500 volts per meter, or you could switch it back if you wanted to, 500 newtons per coulomb. Both are excellent answers. Okay, what is the electric potential at A, B, and C? Okay, well, let's see. I said that the change in potential is 50 volts. Where is it lowest and where is it highest? So if you imagine putting a positive charge here, going this way would be going up the hill because it's going to be attracted to the negative, and repelling from the positive. Or another way to think of it is that if you go this way, you're pushing it against the field. Just like if you're looking at the diagram, if I'm going from B to A, I'm going up the hill. This is where it's lowest. So in fact, it's kind of the numbers of 1, 2, 3, 4 is not really helping us too much here. If I draw down here, if I'm going to say the entire difference is 50 volts, and let's assume then that it's 0 at this plate. Okay, let's make that our 0 level. Then this would be 10 volts, right? This would be 20 volts, 30, 40, I'll put some V's in there, and then this would be 50 volts all the way across. So I made the numbers really friendly, so they jump by 10. So what was the question again? It said, what is the electric potential at A, B, and C? Well, now that we made our diagram, it's kind of easy to figure it out. We can say at A and C, it is at 40 volts. So the potential is equal to 40 volts, and this is assuming that the positive plate, the negative plate equals 0 volts, right? And C or B, well, the voltage would be 10 volts. So I could say V subscript B. So the voltage, the potential at B would be 10 volts. Okay, what is the potential difference between A and B and between A and C? All right, so the potential difference, well, how about this? Potential difference between A and B. Well, I could, how about this for a subscript between A and B? So, well, what's the difference between 40 and 10? Is going to be answer is 30 volts. What about between A and C? The potential difference between A and C would be 0 volts. Okay, what does that mean? That between A and B, that means if I was to move a charge, it would be, so remember, volts is the same thing as joules per coulomb. For every coulomb of charge that I would have to move, that I wanted to move between A and B, it would be 30 joules of gravitational potential energy. So that, or in other words, it would take that much work if I was moving it uphill, or I'd be taking that much energy out of the system if I was moving it downhill. Well, here is actually, we're going to do that. We're going to say, what is the change in the energy stored in the field when a proton, the charge of a proton is 1.6 times 10 to the negative 19 coulombs from B to A. All right, so just like we did this a second ago, I'm going to say, well, the potential difference is equal to the change in the energy per charge, okay, per coulomb. So in this case, we're actually going to be solving for the change in energy. So if I rearrange this, I'm going to say the change in gravitational potential energy is going to be the change in elevation, the potential difference, multiplied by how big of a charge am I going to be moving between those two spots. So we had 30 volts here, right, from our previous question between B and A, and we're multiplying that by, and instead of volts, I'm going to say joules per coulomb, because then my units work out really nicely, multiplied by my charge in this case is 1.6 times 10 to the negative 19 coulombs. So I'm multiplying those two together. We'll go like that so we don't get things mixed up. And I think I can do that. 3 times 1.6 is 4.8. So it's going to be 4.8 times 10, because it's 30, that negative 19 will become negative 18, and my units are going to be ending up as joules, which sounds like a wonderful thing because we're talking about energy over there. Okay, I think we have a little bit more. Let's talk about non-uniform fields a little bit. So, wow, this is a really cool diagram. So these are two diagrams of the same thing. So I did a good job of finding a neat picture on the internet. So we got this positive charge is like, these things actually keep on going up, So there's a positive charge, there's a positive charge. They create potential hills, and here's a negative charge. So uniform fields, just, if we make parallel plates, we have these beautiful uniform fields, a nice constant slope. Here we get a non-constant slope because we can see, hey, up over here, like it's really steep. Over here, it's, pretty well flat. So this is a very strong field there, weak field over there. Okay, so why don't we make up a few spots? Okay, so I picked I picked 3 spots. I labeled them A, B, and C, and first I picked them on here, and I'll tell you how I picked them. I thought, okay, I'm going to pick them between the 40 volt and the 60 volt, so about halfway between those two lines. One close over here, one over here. So again, if you follow that, it's the 40 volt line. It's halfway in between, and C is about over there. So if you can fill that in, and then you might differ a little bit with my. From here, I tried to make the same spots, so I figured A is maybe about there, and B is about there, and C is about there. So for the 3D diagram versus the 2D diagram that has the equipotential lines. So the first question is, where is the field the strongest? In other words, where would the slope on these parts be the greatest? If you look on the diagram on the left, you'd be like, I think B is a little bit steeper than A, than C. It's really hard to tell. Over here, it's a bit easier to tell because you think, well, the ones where the equipotential, where there's the same amount of drop in the shortest distance, that's going to be the steepest. So look at the space between the 40 and the 60 volt lines. Over here, the distance is farther, and over here, the distance is farther. So there's a clear winner when we look on that diagram. So where is the field strongest? I can switch to blue here. I would say B is the... Which way would a positive charge fall from a given point? Okay, so a positive charge is going to fall in the direction of the field. Just to think, it's going to go like away from positives and towards the negatives. So, well, for B, it's going to go this way. For A, it's going to go that way. And for C, it's going to go that way, actually, right? Because it's going to be, look at this, it's going to fall downhill, all right? So how would we describe this? Well, the one way we can talk about which direction it's going to fall is perpendicular to these equipotential lines. So, like zooming in, here's the line, here the dashed line is this way, so perpendicular to it. So I guess perpendicular to the tangent, you could even say, because these are curved lines. So if you've got one line that's like this, and that's the equipotential line, it'll be perpendicular to that one. So that's the first one I think about which way it's going to fall. And the other one is it's also going to fall in the same direction as the field. So if it's a positive charge, right? Positive charge is going to experience a force is the same direction as the field. The last way you can sort of think of it, and these are all the different ways of thinking of the same thing, it's going to move from a higher potential to a lower potential. So you might say over here, like, hey, these numbers? Well, it's going from, this one is 0 to negative 20 volts, right? This is actually going from 0, so it is going from higher to lower. By the way, just throwing this out there, I thought of this right now, if it was a negative charge, it's a bit crazy, but it's the opposite direction, right? So it's gonna fall uphill. So a negative charge in each of these cases, a negative charge would, instead of falling down here, it would go this way. A negative charge here would go this way. A negative charge is going to go that way, or each of these lines. So it would still be perpendicular to the equipotential lines, yep. But instead of the direction of the field, it would be the opposite direction to the field, as the electric field. And instead of going from higher potential to lower potential, yes, you got it. It would go from, not low up, but lower to higher. All right, I hope that was very helpful for you, and as always, I will see you in class.